And for those of you who have just joined or are joining, thank you for attending and for joining us. We'll be starting in just a few minutes. There are quite a few people still in the process of connecting and so forth. So we're going to just give it just a few more minutes. And we have started the recording just so that people know that as well. For those of you who have just joined, thank you very much. We're going to be starting in just a minute or two. There are still a number of people that are in the process, I can see. But we will be getting started in just a minute. And thank you very much for attending. Okay, so thank you everybody for joining our workshop series. This is the first in the series, and after some debate, we decided to start off with a good case study so that people could understand some of the potential in AI applied to water management. And in subsequent sessions, which I'll describe in just a second, we'll be getting into an overview of the series in general so that you have a sense of what's coming up. But before we do that, just to cover some housekeeping details regarding the session. Please keep your microphone on mute until the QA section at the end. Oftentimes, if you just post into the questions section of the Zoom, we'll pick it up. I will be moderating, and so the preferred way is for questions to go there. But if you do need to make a point, please let us know and we can do it. But please do keep your microphone on mute until then. We are going to have time for questions at the end. So we're going to let Manuel and Emery get all the way through their presentation before and this case study that we're going to be talking about before we get to the questions. And we have started the recording already, just so that everybody knows. And the recording will be sent to and made available to all registrants. And we'll be sending out an email with the link to the recording at that point. So you'll hear about it when the recording is ready. And this is the first in our series of an overview of AI in water. As I had mentioned, this session is intended as kind of an introductory example so that you have a sense of what the potential is. With this series, we're trying to focus on the business ROI from AI so this is sort of like a manager's and business person's view of how do I use AI? How should I think about it? What are the possibilities with it? What do I have to do to make it work? We will, of course, be getting into lots of technical details. So this is also a very good overview for engineering teams that want to learn more about AI and want to be able to do work in AI so that they can think about it as well and so forth. But we're very pleased to be offering this. And this session, as I've said too many times probably, is an introductory, kind of a case study just to give you an example and a taste of what AI can do. The next session, which will be in about a month, is a more foundational overview of AI. So in that session, we're going to be talking about the terminology of AI, talking and comparing various technologies, various approaches. to AI. We're going to be talking about what the preconditions to success in AI are. In terms of understanding that, we'll be talking about data and so forth. And at the end of that session, you should be pretty prepared to be at a party and talk knowledgeably about AI. If you've ever felt a little disadvantaged doing that, that session should help. After that, we're going to be drilling into a type of AI called neural networks. They are very powerful, as you're about to see in this presentation, but there's a lot of nuances to them, of course, and we're going to be drilling into that in the third session. We're then going to be talking about how you manage data for successful AI. Data is critical to getting good results from AI, and there's a lot to talk about there. After that, we're going to talk about how you identify opportunities for AI in water. We have some really interesting examples that are kind of non-obvious, but when you start to think about what AI can do, you start seeing AI possibilities everywhere. And then the final session is how you can think about developing your own water AI roadmap. And our goal for this overall session is that by the end, you would understand how to think about AI well enough that you can actually start to develop your own plans. And by the way, we have a number of guest speakers, really great speakers lined up. Manuel is our first, but each of these sessions will have guest presenters as well, helping us help you understand what the possibilities are for AI and how to get it done. And with that, let's move on into the presentation. Let me just start by introducing everybody. So I'm Mike Gardner. I'm the CEO of Akayax. We are a fintech company. We offer tools and technology for cloud data management, which of course is important, critical really for AI success. We also have water accounting software. Emery Capola, who is one of the panelists today, is with NOAA Global Solutions. You're going to be hearing a lot more about NOAA's cutting edge expertise for implementing neural network AI and for implementing mathematical optimization. And our third co-host is Rui Tusi, who's the CEO of Apex Environmental and Water Resources. Apex offers tools and expertise to bridge the gap with technology between the water and environmental industries to get to results through innovative AI, automation, and BI. And we have a very, very special guest today, Manuel Sapiano, who is the CEO of the Malta Energy and Water Agency. And Manuel, please forgive me for taking the liberty of saying this, but Manuel is the person who keeps the lights on and keeps the water running in Malta. And with that, let me turn it over to Emery and to Manuel to go ahead and, Emery, just please say next whenever you want me to advance the slides.
Thank you. Thank you, everyone, for joining us. It's a pleasure to have all of you in this webinar, and we hope that you find this presentation very informative. We're going to touch on a number of issues related to water management with respect to AI and optimization, and how it can empower you to make better decisions and more analysis of your data. So this project took place in Malta, which is a beautiful European nation in the middle Mediterranean Sea, which Manuel will overview a little bit more later. It was a collaborative effort between his agency and NOAA Global Solutions, with participation from Water Services Corporation, the water utility for the nation. Next slide, please. So Manuel's agency, it's a very powerful agency. It's grounded very much in mathematics and modeling, because as you will first find from Manuel more detail, it's a very water-stressed country, and it has a lot of constraints on its system. So they have to be very proactive, very cutting edge in their approaches to managing their water supply and their energy, which is a large part of obviously running water system in a country like that. Next slide, please. So NOAA, we've been around for many years before AI was on probably the mouth of most people that are in this webinar. We thought that there was a real need for AI in the water industry. We conceived this vision actually as late as the 90s, or as early as the 90s, when it was pretty much the stone age of water and AI. And we pursued this vision of trying to bring it to the water industry. And we're proud to have said that we've consulted in nations on every continent short of Antarctica, which also speaks to the problems that the whole world itself is facing with respect to the water crisis that we're seeing unfold right before our eyes. And our team, we have a combination of different experts with a lot of practical real world experience, as well as advanced theoretical knowledge. so we can bring a lot of tools to the table. Next slide, please. So global water scarcity, it's in the news all the time. It's kind of the elephant in the room in some respects, because even though it's well known to be a serious threat to many societies across the world, it's often ignored. Either politics play a role in it, or sometimes just inadequate resources, the combination of factors. But it's something that needs to get more attention, of course, and I think it's slowly starting to get more attention in some places more than others. And as you well know, that there are many impacts that we're seeing as respect to groundwater scarcity and water scarcity overall mismanagement, from saltwater intrusion to groundwater depletion to surface water depletion. One of the more tragic cases we ever worked on was in China, and it was in the Minkin Oasis. It was known as a very, very lush agricultural area that was in the middle of a desert, actually, but it had lakes, had river. And because of over pumping of groundwater, they actually not only dried up their lakes, but they desertified the area, and it's now the largest source of dust storms in Asia. And that actually not only reduced, obviously, the inhabitants' ability to live there, many of them have had to leave. The ones who were left behind, they had to pump water from deeper formations, and that actually had high levels of arsenic, which skyrocketed cancer rates. So there's obviously a domino effect when we start to mismanage our scarce water resources. Next slide. So in the water industry, we're blessed with a lot of data, and SCADA, or supervisory control and data acquisition, was a big part of that. In the 90s, when we started our work, there were not as many SCADA systems as there are today, though I think they were more common than probably people realize. But a lot of the data in the 90s was collected by manually, often every quarter, every month. Maybe people would go out and measure water levels. They would have pumping rates, of course, measured at some scale. But it wasn't until more recent that this data has become so abundant, and yet it's often underutilized. And with this data, there's many ways we can leverage it to do more detailed analysis and provide more accurate predictions, in the end, make better decisions. So we're trying to use this technology to help people understand their data better, understand their system better, and be able to make more informed decisions in real time. Next slide. So how do we leverage this data for improved decision making? So we know that there's enormous amounts of data that many utilities or many entities are bringing into their entities. So they could be collecting water levels, pumping rates, weather conditions, water quality conditions, at all different frequencies of interest. The question is, where does this data go? And oftentimes the data stays in a database. And we've had a number of clients where it was very infrequently would actually look at their data, or they did a very detailed analysis of the data they have to try and understand their system better, try to understand their data gaps, and try to make better decisions in not only just real time, but just longer term planning. Next slide, please. So Malta, as you're going to learn soon, is a really beautiful nation, but that has a lot of constraints because it's a very densely populated country. It's a middle Mediterranean Sea. It's very cosmopolitan, but it also has very beautiful nature. It's a very big tourist destination for many people in Europe. I think it's becoming more known in the United States. And they have the very enormous challenge, Manuel's agency and Manuel, of trying to balance conflicting water and energy related objectives. Next slide. So Manuel's vision and that of the agency is to try and help Malta achieve a real-time decision support system that can use real-time data in a very proactive way, processes data through data-driven models like AI, combined with optimization models to help them identify the optimal operating strategies, both in real time and also for longer term horizons. Next slide. So I'm going to quickly overview, just a very quick overview of what the two technologies are that we're going to speak about today. The first is, of course, AI, or artificial intelligence. This has a deep theoretical and practical history. It goes back to Turing, who was the famous mathematician who cracked the Nazi code during World War II. AI has incredible capabilities when properly used, when it's properly trained, using the proper data. For example, it can make very accurate predictions of water responses in real time, but there's many other applications, of course, that it has. It also has very powerful benefits for in terms of better understanding your data. You can find informed insights into your system that you may not have known otherwise. So it's able to basically analyze huge amounts of data very quickly and give you very powerful insights into your system. Now, optimization is a term that's often used and abused because optimization is actually a very rigorous mathematical framework that was developed by some great mathematicians over 100 years or more of time, and it solves very complex management problems. So it helps you allocate your resources in the most effective and efficient way. An example of that is identifying how to pump your, say, well field at its optimal pumping rates to achieve certain objectives without violating certain constraints on your system. So this bridge that I use in this photo, this is the Minkin Oasis that I referenced earlier, and I think this bridge is a good metaphor of how you can bridge AI with optimization, which is what NOAA specializes in doing. Next slide. So AI is a very powerful tool. It's often called a data-driven technology where it takes data and it learns from the data and it learns to make predictions from the data. When trained properly, it makes extremely accurate predictions, even in real time. It improves your system understanding. It can improve your data collection. There's many offshoots that AI brings that's beyond this webinar itself. But one of the things you're going to see in this training is that it also can allow you to do optimization in a very powerful way. Next slide, please. So like dogs, AI excel at tasks when they're properly trained. And that's a key word, because like any model, if the garbage goes into the model, you're going to get garbage out. And there's a lot of nuances when developing an AI model. It takes experience. It also takes understanding the system. But this is a real quick overview of a classic example where an AI was learned to identify, differentiate. I'm sorry, could you go back one slide? Between a wolf and a dog. And the AI did extremely well when it was trained with the data, but when it's tested with the data, it failed miserably. And it's because the AI, when it was trained, was keying off snow in the background. So when the wolf was in a photo, there was snow in the background, and that's what the AI was learning. It wasn't actually learning the features of the wolf versus the dog. That's a very simple but very powerful example of how you have to be very careful when you develop AI models. Next slide. So this is a artificial neural network, which is one of the most common types of AIs used. And it's basically consists of multiple layers of interconnected nodes. Those nodes are connected by what we call transfer functions, mathematical functions that consist of a combination of the input to the particular node and a connection weight. And during the learning process, when you provide this artificial neural network with data, it processes the data through its network, through its architecture, and adaptively corrects the weight connections in those transfer functions to minimize the error between what it's predicting the output layer and what the actual value is. And that's what we often call the learning process. So it's just iteratively processing this data until it reduces the error to the extent possible that you feel is a stable model. You don't want to necessarily overfit the data, and that provides you with robust predictions. The next slide. This is a very key point. So often when we've worked with, we've done training courses, people often think you just take a huge data set, throw it into a neural network, and it's going to learn. It's not that simple. You really have to understand the physics of your system as well as you can, and any other associated issues with your system. So for example, what data do you have to model the system? What data gaps might there be? Are there ways to fill in those data gaps? Are there temporal issues associated with your data? Are there spatial issues associated with your data? So this is all part of the modeling process necessary when developing a robust AI model. And of course, leave it to Albert Einstein to come up with a very, very salient way of saying something that you really want to think your problem through thoroughly before you go to try and implement a solution, because you can get into a lot of trouble by doing that with any type of model. The next slide, please. So optimization, as I said, is often misused. It's often used as a term that someone is actually doing a trial and error process and are trying to kind of bootstrap what a better solution is than what they're currently using. But optimization is a lot more complicated than that. It actually has a very long mathematical history. It dates back to Carl Gauss, considered by many the greatest mathematician in world history. It goes through a number of Nobel laureates. John von Neumann, who invented the modern day computer, was also a seminal contributor. And I like to use this image of a dog as a good metaphor because the dog is trying to capture this frisbee. And if you think about it, it's an optimization problem. There's a three-dimensional space here. The three-dimensional space in this case is X, Y, and Z. There's a time element involved. There is a trajectory involved. So the dog has to use its own internal neural network to do some kind of optimization analysis as to where the frisbee is moving and what rate it might, what rate it's moving, whether there's wind involved, trajectory, and the dog has to optimize its body control and timing to capture the frisbee. And this is an example of where you're trying to navigate some space, some decision space, and trying to come up with the best solution. So an extension of this would be if you had many, many more dimensions beyond 3 dimensions, beyond 4 dimensions. You have many decision control variables you're trying to optimize. Let's say you have 100 different wells you're operating. Each of those wells, you're trying to identify the optimal solution. It's almost impossible to do that just by trial and error, by intuition. But the formal optimization allows you to identify that rigorously in a very efficient and robust way. Next slide. So optimization consists of generally 3 main components. There's an objective function, something you're trying to either maximize or minimize. So you might try and maximize, let's say, the water quality of your system, or you're trying to maximize the sustainable yield of your system. You're trying to minimize some costs or some adverse impacts. For example, maybe you're trying to minimize the amount of saltwater intrusion to your aquifer, subject to your pumping constraints. And the constraints are what you impose on your system. So you're going to have natural physical constraints, how much you can actually pump, the management constraints, what your water demand is. And then you have the decision variables, and that's actually what you're trying to optimize. Those are the variables for which you're trying to compute. What is the optimal value for each? So how much should I pump each of my wells in order to maximize some benefit without violating my constraints? And optimization can be done either deterministically, where you assume there's no uncertainty, or you can assume there's uncertainty and bring that into your optimization model. Often you require a simulation model, and you can often do not only one optimal solution, obviously, but you can do multiple objectives simultaneously, which we're going to show. Next slide. So formal optimization has algorithms that searches the decision space among the constraints and identifies the best solution. And sometimes, as we're going to present here, you can have a conflicting multiple objective problem. You're trying to simultaneously optimize multiple objectives. And in those instances, what you do is you generate a trade-off solution. From that trade-off solution, you identify the best trade-off solution among your alternatives. Next slide. Now Manuel Sapiano will take over.
Okay, so thanks, Emery, and thanks for that introduction. So I think it's good that we need to introduce Malta as well. So Malta is, as you can see, a small island in the middle of the Mediterranean, so just south of Sicily. And let's say, from a water resources perspective, we're not yes, we enjoy, I would say, a good Mediterranean climate, but that good Mediterranean climate also means a low precipitation and a long, dry, hot summer, which has its benefits, but also has its negative points from the point of view of water availability. Apart from that, Malta is on a country level, is one of the most densely populated countries in the world, and dense population generates a high specific demand for water, because just imagine Malta as being an island city-state. So we're talking of around something over 500,000 people in around a 360 square kilometer area. So there's no hinterland, there's no mountains, there's no rivers, no lakes, and therefore no inland area from where water can be sourced. And therefore, all the demand has to be addressed through the limited land area which there is and the water which collects in that land area. In fact, also being an island, our fresh water is in direct contact with seawater, our groundwater is in contact with seawater, and throughout the years of exploitation of this resource, the seawater intrusion has increasingly become an important problem, and ensuring the quality of abstracted groundwater is an important challenge, because if good abstraction practices are not met, fresh water can be substituted by seawater in the rock, and at the end you still keep abstracting water, but you start abstracting seawater, and that is let's say is not where we want to arrive. Next slide, please. So therefore, it's important also to look at how we do utilize our water resources. First of all, with the challenges of a high specific demand, Malta has, I would say, since the 1960s, had to make use of commercial scale non-conventional water resources, starting with desalination sources, so MSF, moving in the 1980s to reverse osmosis, and later for water reuse. In fact, our drinking water is sourced primarily from reverse osmosis, but when you actually look at all the demand of the island, groundwater still provides around 60% of all the water needs. So this includes agriculture and all the commercial sectors. But looking specifically at potable supply, we can see the operation of the desalination plants. So I would say a good quality water, which however has its energy footprint, and a supply from numerous groundwater sources distributed along the island, where definitely have a lower energy footprint, but good abstraction practice needs to be produced, because if you over abstract from a single point, so you have a high abstraction from a single point, then the seawater can actually upcone, so can form a cone under the abstraction source, resulting in salinization. Interestingly as well, it's not just the public sector which is abstracting, but there's also abstractions from the private sector, and therefore desalinization does not only depend on the management of the source itself, but it also depends on the activities which are going on, so the abstraction activities, but also the recharge activities which are going on around the abstraction source. So there's a number of functions which eventually lead to a result which is visible in the abstraction source. From a practical perspective, so to describe the urban water system in Malta, so we've got the desalination plants, we've got the groundwater abstraction sources. Both of these sources pump into distribution reservoirs where the water is mixed, and consumers receive a blend of desalinated water and groundwater sometimes in a, let's say right now, in a 65 to 35% ratio. So 65 desalinated water and 35% groundwater abstraction. This also means that there's a certain level of flexibility when it comes to the quality of groundwater, because it is being also mixed, diluted, and optimized with the quality of the water coming out from the desalination plants. Next slide, please. Yes, the desalination plants have been a mainstay, have developed into a mainstay of our water supply, urban water supply. However, it is a solution, but it is a solution which comes with its package and with its footprint. First of all, it's energy intensive and dependent also on fluctuations in the price of the energy market. It's around 5 times more expensive than groundwater per unit volume, so it has a cost. Also, that cost depending on energy. Basically, desalination takes fresh water out of seawater, but leaves a concentrated brine, which has to be discharged back to seawater. Possibly not a problem for the small size or for the small scale of desalination plants which operate in Malta, but increasingly a problem when it comes to larger plants and discharge points which are less possibly deep or less or more calm than where the seawater is more calm than what we have in Malta. Also, the energy footprint leads to greenhouse gas emissions, and yes, it's an area which can be tackled also with an increased share of renewables, but still, the energy footprint is important itself, and also there's vulnerabilities, for example, to marine pollution, because whilst the plants do not depend on direct intake from the sea, still they depend to get their seawater from seawells, which are extremely close to the sea. And for example, in the case of an oil spill or a major oil spill, as a precaution, also the plants would need to be shut down. Next slide, please. So obviously, groundwater sustains an important part. So it's around 35% of Malta's total water needs, I have to add, for potable purposes, for municipal supply. When we look at all the groundwater abstraction in Malta, for all sectors, that figure shoots up to 60%. So it's a strategic resource and is a strategic reserve as well. We do the abstraction by water services has now gone down to 12 million cubic meters, but there's around another 18 million cubic meters which are abstracted annually for other reasons, by other abstractors, mainly private, so mainly dealing with agriculture and the commercial sector. And also, if we just look at, let's say, this volume of around 30 million cubic meters and try to see what would be the cost of just replacing it by desalinated water, we would easily add an additional cost to the nation of between 10 and 15 million euro per year. So it has, let's say, apart from just being a strategic resource, groundwater has a cost in itself, so has a value in itself, also by offsetting potential additional costs, additional energy demands, and therefore the importance of maintaining the quality and the capacity of groundwater to keep sustaining water supply in Malta in the coming years. Next slide. So it's an island where we've got sometimes described simply as this floating lands, let's say this floating land system, so a homogeneous system, which it is not. So what we actually have is a complex groundwater system, depending on the variabilities of the geology in different parts of the island, depending also on tectonics, which have resulted in numerous faults and fractures, which juxtapose different formations and different formations with different permeabilities, one with each other. So therefore, looking at the aquifer, so looking at our mean sea level aquifer, it's quite a complex system to actually manage, because different parts of the aquifer system actually respond and have different response functions to abstraction, yield, but also to the response in terms of salinity. And also, let's say, it's not just used for public abstraction. So as I said, the groundwater is also used by numerous sources for private supplies, such as agriculture, distributed sources, not abstracting the volume per source, which water services abstracts, but still on a large scale, contributing to a, let's say, significant volume, which also affects the balance between freshwater and seawater, and therefore affects the potential for seawater intrusion in different parts and different regions, depending on abstraction density. Next slide. So this actually, when we were looking at this project, we tried this pilot to try to see the value of AI, the value of trying to look at how the let's say the part of our abstraction system could actually respond to variabilities in abstraction, variabilities in different climate, and how, let's say, if the quality of the abstracted groundwater could actually be predicted in terms of salinity before the upconing or desalinization happens. So what predictive value, what predictive functions can go on? Because one aspect which we wanted to look at is particularly if certain conditions which can be predicted, which can be put in a model, can actually define what quality, what would be the impact on the quality of groundwater abstraction. Because first of all, one could look at taking a proactive approach and possibly limiting or reducing abstraction during particular periods when groundwater sources are actually more prone to seawater intrusion than other periods, depending on what's happening also around them. And also, from an energy and a cost perspective, how optimization could also look into the most cost-effective blend, considering cost and quality, which can be obtained from the system. And therefore, with this exercise, we tried to have a viewpoint on how AI and how optimization systems can be used, how they can be applied in Malta, and how can these modeling systems actually help us in a practical way to protect the quality of groundwater abstraction sources. And I believe, Emily, from this point on, I will pass on the floor back to you.
Thank you, Manuel. Thank you for the background. Next slide, please. So Malta's management challenges were we wanted to try and see if we could minimize the combined energy consumption of RO and groundwater. So as Manuel explained, RO is significantly more energy intensive. It's about 5 times more expensive than groundwater. But the trade-off with pumping more groundwater is you draw salt water into your aquifers, which salinates your water supply, which is obviously negative for the consumers of the water, and you start to diminish the overall quality of your groundwater system moving forward. So we want to try and balance 3 objectives simultaneously, all under the constraints of the management constraints and also weather uncertainty, which is related to water, which drives water demand uncertainty. Next slide. So we took this large gallery, which is about 300 feet below the ground surface. It's called a gallery. It consists of these horizontal tunnels about 1,000 meters long that radiate out from the center like spokes on a wheel. And from these tunnels, they pump groundwater. And the advantage of using tunnels like this is you kind of reduce the saltwater upconing to some extent. It's not like a vertical borehole. So you're skimming water off of the water table, but still, because they pump so much, it is going to have an effect on the saltwater quality of the system. So what we did was we took data from this particular gallery and we did variables that included chloride data, weather conditions, extraction rates of public and private wells. We wanted to see whether we could predict chloride concentrations at this location 1 month into the future. We had 5 years of data. Next slide. So we developed the model. This is just an overview of our system. So we essentially take data from the real world, we process the data, pre-process it, we develop our AI models, we look for sensitivity between variables and try and refine our model. Once we have confidence in our model, we then combine it with formal optimization, where you combine the AI model with our optimization model, and we then identify optimal decisions, or we generate trade-off surfaces from which you can identify optimal solutions. Next slide. So this shows you the pumping station itself. This first graph on the left depicts the chloride concentration in the gallery over time versus its daily flow and its weekly flow. And the big takeaway from that is that there was no correlation between what the gallery was actually pumping over the course of the month versus, or weekly flows or daily flows versus what the chloride concentrations were at any given time. So you couldn't just do a simple interpolation or linear regression. It was far more complicated. That's undoubtedly because there are other wells that are pumping near this gallery that you have to incorporate into your model. So we did that. We took a number of different pumping sources, actually quite a few. We have different ways of incorporating them into the model. We took weather conditions and other factors, and we're able to, with limited data, still develop a very accurate model that is able to predict chloride concentrations on average very accurately 1 month into the future, even when there are very dramatic changes over 1 month periods. And again, this is over a 1 month period with limited data. So with more frequently collected data and with more data, it'd be undoubtedly the AI model would predict even more accurately. But anyone who's accustomed to groundwater modeling and saltwater intrusion knows it's an extremely difficult problem to accurately simulate, especially in a very complex limestone system that Manuel was describing, where you have significant geologic features. You could have karst features where there's dissolved caverns, and you have significant heterogeneity where the geologic conditions change significantly over space. You have anisotropy that change significantly over time. To incorporate all those features to a physical model is really impossible because one, you're not going to have the information, and two, your model is only going to be a simplified representation of the real world. Next slide, please. So once we did our models, we could then do optimization. And this is a simple two-dimensional trade-off where we did two objectives. We want to minimize the combined chloride concentrations of the two water sources versus a total energy consumption. And those points along that graph are trade-off solutions where you're finding, based on how much weight you're giving to one of those two objectives, what the optimal solution would be. And each of those points actually represents exactly how much you should pump each of your 55 or 56 wells and how much you should produce with your RO plant to achieve those objectives at their combined maximum extent. And you can then use those points aligned to draw an actual line and select any point along that line as your optimal trade-off, which becomes a matter of priority and preferences of the decision makers. Next slide. So this is a three-dimensional optimization problem that we then did, where we took three objectives that we simultaneously optimized to delineate the trade-off surface. So in this model, we were trying to minimize the amount of saltwater intrusion from pumping of our production wells and the gallery. We're trying to reduce the combined energy consumption of both the RO and the groundwater, and we're trying to minimize the mixed chloride concentrations, and we included weather uncertainty. And this surface that you see on the graph, that is actually the trade-off surface. So those represent any points along that surface is an optimal solution for any given trade-off between those three objectives. So it'd be left to the decision maker, and there's different ways you can do that, to identify where do we want to be along that surface. So very quickly, for example, if you're in a drought, if you're in an extended heat wave, and you have a very high energy draw because people are trying to stay cool, you're using air conditioners, then you might want to minimize the amount of energy you're using for RO production. So you'll reduce the amount of RO production you're using, you'll increase your groundwater pumping, but you want to increase your groundwater pumping in such a way that you're going to minimize the amount of saltwater you draw into your aquifer and the amount of saltwater that's provided to the consumer. Next slide. So the study outcomes from this pretty extensive study, we achieved a much deeper understanding of the system in terms of what variables seem to drive what effects. We were able to make recommendations for improving their data collection, which the agency is doing, has implemented. We've developed some very accurate AI prediction models for salinity and water demand. We developed a framework for optimization, both with uncertainty, where you're simultaneously balancing multiple objectives and how to operate both your RO and your groundwater. And then this can move forward once they have the data in place to make it a real-time decision support system where they can then make decisions that are using data streaming from different sources in real time, including weather. It could be water quality conditions in real time. It could be water level conditions in real time to optimize their system conjunctively. Next slide. And questions.
So if anybody of the attendees has any questions, please post them into the Q&A window, or you can raise your hand and we can take them that way. But I have a couple questions just to get things flowing, basically. Manuel and Emery, maybe you could tell us a little bit about some of the challenges that you've kind of explained the process and summarized the success you had, but could you talk about some of the challenges that you had in implementing this and along the way?
Could I, would you like, I will go. So Manuel's group, they're incredible because they have really sharp people that were able to assimilate the data. So they have enormous data sets. I can't even begin to represent how large data they have. They're not just recording their own public data, but also the private allocation. So all the private wells that are on the island are supposed to report their data, and I think it's once a day. And the agency actually measures their pumping rates I think every few minutes or every hour. Then they have water levels, they have water quality data. So you had enormous data sets that had to be assimilated and organized so that we could then start to develop our models and analyze the information as best as we could. And it's somewhat of an iterative process because when you collect the data, you start to do your analysis, and sometimes the data tells you, or the models tell you, certain things about the data or the system. Then there's a somewhat of an iterative process where you then go back and you request more data. But I would say the biggest challenge is the data, which it all starts with. You have to have the data in place. You have to organize the data. It has to be QA/QC, which is a rigorous process. And again, the agency was really superb in doing this. It made our job much easier. They gave us the data in a very nice formatted way, after which we could then process the data for our models and our analysis. So I would say the biggest hurdle is probably that is the data itself. Would you say? I'm sure Manuel has much to add.
Yeah, basically, when looking at the systems, one way of describing them is data-hungry systems. So, yes, and I would say each level of optimization would not just require another level of data, but would require a squared increase in the level of data. So that's a challenge, particularly when you need to look also to the resources to manage data. And sometimes it's not just data, but it's how to transform data to useful information. And that's when, let's say, systems start also to creak because resources are what they are. So this was a one-time pilot. There could be, let's say, we could put in resources for this one-time pilot. It was a learning curve on how data can be managed, how data can be prepared, stored, and everything for also the future, for possible initiatives related to the application of the technique. But yes, managing data is definitely the major, I would say, I wouldn't call it bottleneck, but is the major part of the work which applying these systems would require. And therefore, the usual, I would say, easier said than done, balance between the accuracy of the model vis-a-vis the data needs which the model would require.
Manuel, I have a follow-on question for you. We have a question from the attendees as well, which we'll get to in just a moment. But I have a question for you as a follow-on to that. With your board of directors and your management and maybe even the government of Malta, when you explained to them that you were planning to use AI to help, assess the situation and help with the planning, were they receptive to that, or were they initially skeptical? Were they excited? Were they were they dismayed? I mean, just maybe you could just help us think through kind of like how you what we would say in the United States, how you socialized the idea that you're going to use AI and so forth.
Look, let's start with one thing. So I would say we've got quite an approach which is ingrained in reality. Like Malta, the size of Malta is what it is, and definitely we're not technology developers. Throughout the years, however, even if you look at our water policy and our water management plans, there's been a lot of uptake of emerging technologies, possibly their adaptation, with the challenges with adaptation of technology brings about. But if we look at desalination itself, optimizations in desalination, water reuse, leakage management. So most of these are not technologies which have been developed in Malta, but which Malta was at the forefront of actually adopting and testing. The size of the island makes it feasible to act as a pilot because it's even assessing a pilot on a national scale with all the, let's say, issues which implementing something at a national scale brings up. And this approach of actually testing technologies, adapting, has left quite an open approach to, let's say, testing, whatever is out there which can be used to optimize water management. So usually you don't find a closed approach. So one better still when actually we're talking about using what we already have and possibly having advice on how to monitor or, let's say, get data, get your prime hour systems to get more useful data. So this in itself and this open approach, yeah, there wasn't some, let's say, that specific or that focalized resistance to actually using these types of techniques, as there was not resistance throughout the years to adopting different types of technologies. Obviously, moving then towards adopting, let's say, from the pilot size to adopting on a large scale, where investments would be required for, let's say, data collection or the optimization of a whole production distribution system, which requires a cost and also which entails significant, let's say, significant work, then that's something else. It's not a no, but there's a time frame when these upgrades can be implemented in parallel with other needs when a growing population and a growing demand actually require also investments or keeping up the investments in production and in direct management of distribution as well. So it's quite a balance between what the priorities are. However, let's say there's usually in Malta there's a lot of openness for testing technologies, learning from them, and yes, looking forward to plan on how to eventually apply them.
That's wonderful. Thank you. We have a couple questions from the attendees. Maybe we could turn to those. I think perhaps this first one would be good for you, Emery, but from Xiu Lo in the attendees, she's wondering about stochastic modeling to incorporate weather uncertainty. What can you tell us about that, Emery?
So you can look at, you develop your models. For one, you have weather uncertainty that's inherent. So you try and quantify how much uncertainty you have in your weather forecasts based on historical forecast information versus what actually occurred. There's also going to be some inherent statistical error with respect to your model itself. So you could have perfect information, run your models and see how much they might deviate in terms of water demand. So we're trying to forecast water demand as a function of weather conditions. So one, there's inherent uncertainty associated with the weather itself, what the forecast predicts versus what actually occurs over different time frames of interest. And then even if you have perfect information with your AI model, you're trying to predict water demand, there's going to be some error between what your model actually predicts and what the demand is. In our case, we achieved a very high accuracy, but there's still some deviation. So you try and combine those two elements of uncertainty into your stochastic optimization model, and then you solve it, and it actually generates basically a probabilistic forecast of optimization. You can then use to then try and couch your solution within some confidence interval. So we recognize that a lot of these systems are pretty much any hydrologic system is not going to be deterministic. There's going to always be some statistical uncertainty. And even if there's not uncertainty in the system itself, there's going to be some prediction error with your model because it's never going to be a perfect representation or be able to account for all the different factors that are really driving your system.
Thank you. We need a couple minutes at the very end to wrap up, and we do have a couple other questions, so we'll have to keep the answers brief on this. But The first one is from an attendee wondering about the relationship between optimization and AI, and more specifically, what AI technology was used, and then what the AI was used for, and how they related. So, Emery, an example might be, was the AI used to determine parameters that could then be used in an optimization model? Or, what was that bridge, if you will, or how, what was the relationship of the optimization to the AI?
Right. That's a great question. And I just very briefly touch on the beginning, that bridge, the Minkin Oasis in China between AI and optimization. So AI itself, when it learns, that's an optimization problem in itself, where it's optimizing the weight connections. So for the AI, we were predicting chloride concentrations in groundwater in response to different pumping rates and weather conditions, for example. And that itself would qualify as a model. So it's a predictive model that we use to predict saltwater intrusion or saltwater conditions at a given point in space in response to different pumping and weather. Now, what do you do with those predictions? So let's say we have not just one prediction, we're trying to predict or optimize the effects of multiple wells or sources that are removing water or treating water. We take those models and we incorporate them into an optimization model. The optimization model is a mathematical formulation of your management decision system. So let's say we're trying to minimize our total combined saltwater intrusion, or we're trying to also minimize our total combined energy consumption of our groundwater and reverse osmosis sources. We would incorporate our prediction models into that optimization model, and they serve as constraints. They're really simulating the system itself. And in combination with your management constraints, for example, what your water demand is, et cetera, the optimization model then solves, or the algorithm solve that formulation and identify the optimal trade-off solution if you're doing a multiple objective problem. If you're doing just one optimization or one objective function, let's say we're trying to reduce energy consumption, it would just explicitly give you one solution for that particular problem. There's only one objective you're considering.
Great. And then we're going to be very, very brief, but the question that I inadvertently dismissed, and apologies for that, but with more data, would the accuracy of the AI predictions erode into, is more data a problem in essence, or is more data good?
No, as Manuel said, these models are data hungry. So the more data you can give them, the better they're going to learn, just like humans. So the more events you can provide the neural network with, the more it's going to be able to learn behavior that might be, say, more extreme or more anomalous. The other thing to remember is when we developed this model, it was for 1 month ahead, which is a long prediction period. And we were using relatively sparse pumping data. When I say sparse, temporally sparse, it wasn't, we were using, not as much data as we would like to have used, let's put it that way. So if we have data collected more higher frequency and shorter prediction periods, you're going to get even more prediction capability or higher prediction accuracy. But the beauty of AI is you can do models for any number of prediction periods you're interested in. You can do it by hour, by day, by week, by month. You can simulate years into the future. We did that in a project with a consulting company in Provincetown, Massachusetts, where we ran a neural network, and it actually reproduced salinity concentrations over a 4-year period, 46 months actually, using monthly stress periods. So, but in general, yes, AI loves data.
Great. Unfortunately, we're out of time. There's at least one more question. We will be we are here sharing our emails. So if you do have any questions, we welcome them. We also welcome any suggestions or thoughts about this. Our intent is to deliver value to you, the attendees, in terms of what you would most like to learn and so forth. So if you have thoughts about the sessions or additional topics, we can always add more. Please send us your ideas and suggestions, but also, of course, questions. So Patrick Wickham, feel free to email Emery or any of us. And Emery may actually want to respond to you. I think we have your email from the registration. But just to mention again, the upcoming sessions, next month on April 11th at 11 a.m. Pacific time, we will be going into a more general overview. Again, that will be presenting foundational concepts in how to think about AI, including taxonomies of technologies and approaches and so forth. We also will be announcing the dates over the next month for the sessions after that. And at the beginning of the recording, if you missed it, there was a kind of a run through about what we're going to be covering, a few more details about each of these. And then finally, thank you for attending this session. Please do pass the word on if you know of anyone who would be interested. We will be sharing the recording out to all registered attendees. The recording will be an accessible link that is open to all. So if you have colleagues or people you know that might be interested in the recording, please go ahead and forward to them, and they're welcome to look at it. And again, if you do have any questions or suggestions, please let us know. And thank you very much for attending. It's been a pleasure, and have a great rest of your day. Thank you.
Thank you.
Thank you, everyone.
Oh.